So in this unit we will cover reinforcement learning. And here again we will venture into a new territory where we will take away the supervision in a way we've done in the supervised section. Instead of getting feedback for every action you are taking, the agent will get the feedback at the very end. One of the most exciting examples of reinforcement learning is the recent success of machine playing AlphaGo. And again, in this case, we don't give to the machine a reward for every action, but what counts whether the whole game has been successful or not. So we will start approaching the problem of reinforcement learning by looking at a more simplified scenario, which is called Markov decision processes, or MDPs, where the machine needs to identify the best action plan when it knows all possible rewards and transition between states. Then we are going to lift some of this assumption and look at the case of full reinforcement learning, when we need to really, be in the world, collect the rewards, experience different transition where this information is not given to us, which is a typical case in life. And at the end of this unit, you will have a chance to test many of these ideas as part of the reinforcement learning project, where you will implement an agent that can play text-based games. So today we will talk about reinforcement learning. I'm sure that all of you have heard about reinforcement learning because of the recent successes of AlphaGo, where we had machine which beat a world champion in the game, and it was so super exciting. So reinforcement learning is different from supervised learning, both in terms of tasks you can solve with reinforcement learning and the whole intuition behind it. So in supervised learning, we assume that when we're teaching our algorithm to do something, we're giving to it supervision at every single step. However, in many problems in life, you cannot get supervision at every point of the progression. You go, you try different things, and eventually some of them succeed and some of them don't. And as intelligent human being, you actually know to trace back and attribute what made your whole exploration successful. So again, if you want to think about animal learning, when we teach, let's say, a mouse to run in the maze, the idea here is that the animal doesn't get a reward at every single step, but at the end, when the animal reaches the goal, then it gets a banana or whatever reward they give to the animal. So in many situations in life or in our engineering tasks, we are actually faced with the same scenario. So the first one, as already mentioned, is computer games. When computer tries to play another human or against a computer, in this case, you may get some rewards in the middle of it, but actually what counts whether the game was won or not. Similar, you can think about teaching robot to solve some complex navigation task where the robot needs to go in some terrain, reaching the final point. Again, the robot can get some rewards in the middle, but actually what counts whether the goal was reached or not. And I want to make sure that we understand that the tasks related to reinforcement learning do not necessarily correspond only to kind of navigation tasks or games. Many of our daily activities can be thought as reinforcement learning. Let's say you are in a marketing company and you are trying to recruit a new client, and you have multiple options that you can take. You can call them, you can send them email, you can send them personal email, maybe you can send them a gift. There are lots of ways to engage with a customer. Each one of them would come with different costs, and maybe the customer would like to get a gift better than getting your email. But you would not know what is the right action at the time of you taking it. What you would actually want to make sure that at the end, what counts whether the customer signed up or didn't. So this is the type of problems that are related to reinforcement learning, where our agent can take a lot of different actions, and what counts is the reward that this agent gets or doesn't get at the end. And the whole question of reinforcement learning is how can we get this ultimate reward that we will get and propagate it back and learn how to behave. So that will be the topic of our discussion today. So I kind of introduce you the type of problems we can solve with reinforcement learning. And the next point of our lecture will be discussing how to formalize these problems, because we need to start talking about it in a clear mathematical terms. And here I will talk to you about Markov decision processes first. Markov decision processes. And within this big category, we will talk in more detail what is the notion of state, of reward, of action, and so on. Once we completed this discussion, we will start talking about what is called Bellman equations. These equations would enable us, again formally, to describe how we can propagate the goodness of the state from the reward state to all the other state and to all the other states. And based on this discussion, we would be able to formulate value iteration algorithm that can solve this Markov decision processes, and I would call them MDPs. MDPs, okay. So this is a plan for today. So let's start talking first about Markov decision processes. And even though when I started the lecture I gave you all these exciting examples of reinforcement learning, let's just look at some sort of maybe boring example, but it's in a clear example on which we will do all our introduction of the terms. So assuming that you have a very simple world, you just have here different states and your robot can move around this space. And let's say this is a place where the robot cannot go through because there is some hazard over there. And if the robot did the good job, it would eventually end up here and get reward +1. And if the robot not fail, but if the robot end up here, it's going to get a negative reward or punishment. Okay? So your goal is to kind of find a strategy to get to this particular place where you're getting all the rewards. So let me first start introducing the terminology on which we will be talking. So the first piece of terminology is talking about states. So states, we will call them consistently S when we're talking about the individual state, and they all come with some set of states, capital S. And for the sake of our conversation today, we will assume that all the states observed. So in this case, again, I have 8 states, and the robot, or in this case I would call myself I know exactly where I am standing. So it's called observed case. Doesn't have to be necessarily this way, but we will assume that everything is observed. Okay? So I would say observed. The next part of our description would be action. What you actually can do in this space. So we will have actions, and I will call them consistently lowercase a. Okay? And what are those actions? Those actions are things that you're allowed to do. So in this case, we would assume that the agent can go left, right, up, and down. Okay? Those are the 4 actions that you can do. And let's say if you're taking an action and you're hitting the wall, you're staying maybe in the same place where you are. So this is a very small world. If I just defined you that and just explained to you saying, what is a big problem? You know, let's say I'm here, I just need to go around and I'm getting 2 plus 1. What's so special about this problem? It's just a planning problem, you know. There is my starting state, there is my destination state where I'm getting the highest reward. Why do we need to introduce some new machinery? Planning will do it for us. However, what's interesting about it, that we are operating in non-deterministic world. Non-deterministic world means that maybe I want to go straight, and I would eventually end up going straight, maybe in 80% of the times, but there is 10% chance that I may go right or I may go left. And that's what makes this problem particularly interesting, because even though you may have good intention and you know where you want to be in, but you may end up being in a different place. It's exactly like in life, correct? We have good intention but may end up somewhere else. So that's why we will introduce a new notion which is called transitions. So transition will take state from which you start, then the action A that you are taking, and the destination state, okay? And it will give you probability of ending up at state S prime when you have taken action A from the state S. This is a transition. So for our case, we would assume that we have 80% probability to follow the direction which we intended to take, and then there will be a 10% chance that we will go to the sides. So you can imagine yourself creating a very big table that say that if you are, let's say, in this state and you take this action up, 80% you're going to end up here, 10% you're going to end up here, and 10% you're going to stay in the same place because there is nowhere to go. Okay, so this is our transition function. And the final thing that I want to introduce you is a notion of reward. Okay, because we said that this is our way to see what is a good behavior, if at the end we got a reward. And there are many ways to define reward. So what I kind of implied here, I told you that if I'm taking, the only reward or punishment that I'm getting are in these two states, so I can define reward as a function of state, okay? In other problem, this definition is not sufficient. Like, for instance, in the examples that I gave you from the marketing case, you actually not only care where you end up, you also care, how much it costs you to do something. So maybe in this case, you may want to define reward as the function of the original state, the action, and the state where you end up going. So whatever I'm going to be describing today will work both with this reward or with this reward. Both of them will be totally acceptable. And when we're talking about Markov decision process, we're actually thinking about, we would assume that both the states, action, transition, and rewards are given to us. So pretty much we can say that MDP, Markov decision process, is just a quadruple of all these values. So it will be S, A, T, and R. And you can add some extras to it. For instance, you can assume that there is some starting state where you have to start. Doesn't have to be so, but you can decide that there is some starting state. You can also assume that there are some states which are kind of halting states, that once you arrive there, you cannot continue anymore. Once, let's say, you arrive here, you got your +1 reward, you are done. So there are all the extra variants of these problems that you can consider, but everything that we are discussing will be applicable to all these different variants of the problem. So for now, let's just look again at what is MDP. So in this case, we have a set of states, we had a set of actions, and you can think about this transition just as a very big table that gives you a probability for every triple of state, action, and another destination state. And finally, you have a reward, which can again be written just as a table of values. Now, when we will start thinking about more realistic problem, when we want to have a more complicated definition of transition function and the rewards, but for now, for what we're discussing today, you can just imagine it as tables. Okay, so now we define kind of the basic language of our discussion, and then the next question is, how can we think about rewards, correct? Because what I told you, that ideally when I'm thinking about reward, there is this final reward. But in many problems, you actually want to give some kind of reward in the middle. For instance, you may give some living reward, where you need to pay some price for making a move, so you don't go endlessly round and round. Or as in the case of marketing, certain action costs you differently, so you want it all to be encapsulated in rewards. So typically in reinforcement learning, we are discussing about kind of the strategy of how to aggregate rewards using the language of utility functions. Utility functions. So what would be the utility functions? So one option for utility function is to say, let's just go collect all the rewards, sum them up, and that's it. And the problem with this approach that in this case our agent can actually collect an infinite number of rewards, and if it is infinite and you have two different strategies, there is no way for you to compare between the two. So ideally we would want our utility function to be bounded in some way. And maybe the most obvious way to bound them that we can think about, it's what's called final horizon. So the idea of final horizon is very intuitive, that you can only collect the reward for some number of steps, like say 10 or whatever number you decide, and whatever happens afterwards doesn't count. So in this case, this is our U for the utility function, and it's defined of a sequence of states from S or 0 to S n plus k. And we would assume that for any value of k, we are just collecting the reward for n steps. Okay? So it's like you have a final number of chances to collect your reward, and what you do afterwards doesn't count. Now, there are multiple problems with this definition, even though it kind of sounds intuitive. So one of them is that actually your behavior becomes in some way non-stationary. You're not only depending on which state you allocated, it actually depends on the time point where you arrive there. So if you arrive to this state and you just have one step to go, you may decide to take a very different step versus if you have many, many steps to go and you can do a lot of different things. So for instance, if you just have one step to go, you may go to extremely risky behavior because you have no other chances. And what I want to say that the reason actually we call this Markov decision processes by the name Markov, like similar to Markov hidden models, that we actually want to have all our representation to be encapsulated in a way that our behavior only depends on the current state. So the outcome of certain action would only depend from the state where I started and not from the time. Any time when I arrive to this state, there will be the best action for me to take. And if we will adapt this time of utility function, it would disable us to do it, because we are not only depending on the state, but we will depend also at the time point to which we arrive to the state. So we will not be using this definition. Instead, we would use something else which is called discounted rewards. Discounted reward. So the idea here is that I still want to have my reward, my utility function, to be bounded, even if the agent can go to an infinite number of states. So the way we will achieve it, we will kind of make our agent behave to some extent like us, meaning very greedy. We would say that we really value the reward that we are getting now, but we value less the reward that we may or may not get tomorrow, and even less the reward that we may or may not get in 2 days. So you can think about it when you have an option to watch a movie that you really like, or prepare for a class which will eventually bring you a good grade. Many people, maybe not you, but many people would prefer to watch a movie. So that's exactly what we will make our algorithm do. So when we are looking at the current horizon, we are going to get some reward, immediate reward, in state as 0. Whenever we are thinking about reward that we are going to get in the next step, we will just weigh it by gamma, where gamma is some value from 0 to 1. So in this case, it's going to be gamma multiplied by the reward in S1. And then we will have gamma squared for the next one, and so on and so forth. So what's interesting about it, in addition to the fact that it emulates the behavior of some of us, is the fact that it's actually a bounded reward. So the next step for us is to look at this expression. I'm just going to fold it as a sum so that you can close and see where we're going with it. So here we are going for t from 1 to infinity, gamma t, and reward in state t. Okay, so here nothing happened, we just wrote it in a different form, and now things will start happening. So the first thing that I will do, you remember I'm trying to get a bound here, I'm going to substitute all these rewards with a maximal reward. So now we're not using equal, we're already bounding, and if I substitute all of them with the same maximum reward, I can just take it outside of the equation, so it's R max. And here we have a geometric series of gamma t. And what we know that this expression is actually equal to 1 divided by 1 minus gamma. So what we will get here is R max divided by 1 minus gamma. And this is a bound. And what you will see is that actually the fact that we are using this discount and rewards would be essential for us to make our algorithms converge. So this is the discounted reward that we will be using for the duration. The next thing that I need to introduce you before we can move to the algorithm, you can see we're doing a lot of introduction, but this, I promise, is the last one. We need to talk about policy, okay? So what is policy? Policy is an optimal action that you can take in a state, okay? So you can say policy, and I will put a star here, which means an optimal policy. For every state, it would tell me which action should I be taking. And the idea here is that you want to maximize expected reward. Because whenever you're taking the actions and you're taking the whole sequence of action, you actually don't know which reward you're exactly going to get, because you remember the world is not deterministic, you have intention to move forward, maybe you're going to move sideways and so on. But the idea here that we want in every state to select an action which optimize the expected, maximize expected utility. This is our goal. This is called policy, okay? And now let's go back to our original examples that we have over here and try to come up with different policies. And what I want to say here is that policy would very much depend on the structure of your reward. Let's say in this example, I still have +1 for this state and -1 for this state. But in addition, for every transition that you take, each time when you take an action, you're going to be paying some small price. Let's say you're going to be paying minus 0.001. Okay, so let's imagine how the policy, I would obviously kind of unofficially do the computation, but roughly speaking, the policy in this case is maybe gonna go this way. Okay, this is one policy that we would expect, we will try to get as soon as possible to +1, and at the same time try not to go directly and encounter this penalty. Now, let me, and this was the case of our living reward being equal very, very small negative number. Now, imagine that my living reward will be really atrocious. Let's say I would assume that I have to pay -10 for every step I am taking. If I am paying -10 for every step, this will not be a good policy, because while I'm going from here to here, I'm encountering huge penalty. So in this case, you may want to directly jump here, correct? Because you don't want to go around. And in every single place, the only thing that you're going to be optimizing is how shall I get in the smallest number of steps to this +1. So you can see, depending how we would define reward, we would have different policies. But the point that I want again to emphasize to you, notice here, let's say you're looking now at the blue policy, okay? When we're thinking about the blue policy, at every step, independently of how did I arrive to this step, I have the same one action that I am taking. And if we would have went with a finite horizon, we could not have done it. It will depend where we are in our journey, which time step. Here it's independent. Each time when you arrive to your state, your policy would tell you where to go. That's when we are talking about solving MDPs. When we're talking about it, we're talking about finding the policies. That's what it means to solve MDPs, to find the best way how to act in the world to maximize expected reward. Okay? So now we finished talking about MDPs, and the last thing that I want to say before we move forward is just to connect it to the reinforcement learning story. So here, you see, when we're talking about MDPs, you're thinking, is it the same as reinforcement learning? So in principle, the general idea of thinking is the same. The only difference will be related to the fact that when you have a reinforcement learning problem, you're not provided with a transition function and with a reward and the reward function until you actually go in the world, experience and collect it. So we will see that a lot of machineries that we will develop today when we are talking in Markov decision processes would help us to think about reinforcement learning problems. But again, for today, we assume that all of those are given and we need to solve it, meaning to find the optimal policy for our MDP. Okay, so now I will start talking to you about Bellman equations and introduce you a tiny bit more notations related to these Bellman equations. Before we go into notations, and it's like there's so many of them, we are gonna intuitively understand where are we deriving, okay? So what is the intuition here? You need somehow to have a mechanism to propagate your reward. So let's just for now assume that the living reward is 0, that you have here +1 and -1, to make it very simple. You know this is a great place to be, correct? Because you are really getting a reward. You know that this one is also a great place to be because you are just one before the reward and there is nothing bad that can happen. So this is maybe not as good as this one, but kind of really great space to be in. This one maybe not, the greatest space because you still need to traverse it until you're getting there. So we need to provide our agent with some quantification is how good is the state, what is the value of the state, so that it can orient itself. Even though my reward is coming many steps ahead, I know that this is kind of a promising way to continue. So that's why we need to introduce some notion that will remember for each state what is the value of the state, how good this value is. And what the Bellman equations do, they actually connect this notion of this value of the state and the notion of policy. So now we will start introducing a tiny bit more notation, just 3. I promised to discuss Bellman equations. So the first notation that I will introduce, as I already alluded, is called V star. This is the value of state. What does it mean? It tells you the value of the expected reward if you're starting at state S and act optimally. It's like, what is the best I can do when I'm starting in the state S? And as I alluded to you previously, maybe the state which is next to our reward would have higher value than the state which is very far away. So it's expected reward starting at S and acting optimally. So in this case, instead of saying acting optimally, I could have said acting according to the policy. That from that point on, you're doing the best you could. Now I'm going to introduce you something which will sound a tiny bit counterintuitive, but we will see the value of it. So now I am going to introduce something which is called Q value, again star because it is an optimal one, which will be defined on state and action. Because here, I don't actually care which action I take. I assume that somebody tells me what is the best set of actions. Here, I'm decomposing it and stating that it will be an expected reward if I'm starting at state S, taking an action A, and then acting optimally, or acting according to the policy. So, expected reward starting at S, this is like before, then taking action A and acting optimally afterwards. And acting optimally until the end. Okay? We already seen our policy. I will just remind you and say that we also have our policy pi, which we shouldn't forget, correct? This will be our policy pi, which takes S and returns us the best actions that we can take. Okay? So those are the 3 quantities. And what the Bellman equations do, they actually connect all these 3 quantities together. So let's start first by connecting the value of the state and the Q function, okay? And the Q function. So we can say that the value of state S is going to be, as we said before, the value of the state if we start at state S and act optimally. So towards this optimal behavior, we need to select the best possible action. So pretty much what we can say that it's going to be max A QSA. So let me explain to you. So from this state, you can take many possible actions, but you say, if I want to continue acting optimally, I need to select the best action. And to do so, which are the best action, I'm going to try different Qs with different possible A's and select the one which gives me the highest Q. Okay? Another way to write it, we could have just written it, it's going to be QS pi star S. So this just tells us, instead of explicitly showing that we're selecting the best possible action, this is the action that should be written in our policy. Our policy will tell us what is the best action to take. Okay, so this is the definition, this is a connection between V and Q. And what I will do next, I would recursively define the values, the value of V. So what we would say, that when we're actually maybe, yeah, let's start with Q. Q would be easier to start. Let's start with Q. So in this case, we are in state A and we took an action A. I will start explaining to you as if we deterministically know where I will end up. Let's say my transition function tells me that whenever I'm in state A and I take action A, I'm always going to be at the same exact place. So in this case, what I know will going to happen. So whenever I took my step, first of all, I'm going to collect the reward. I am going to collect the reward, okay, plus I'm now in a new step and my value would be dependent on whatever I can collect from that state, correct? I am now end up being in some state S prime, and I want to see what will be my best expected reward when I'm going from that S prime up to the end. So here we are going to write V S prime. There is something missing here, and it had to do with the definition of discounted reward. You remember we said that we value the current reward more than the future reward. That's why whatever we are going to collect from the state S prime, we will weigh by the gamma, by the discounting. So again, we are taking our path from state S towards, our completion. We are dividing it. We are stepping one step to state S prime, collecting the reward and saying, and whatever you're going to collect is going to be determined by the value of state S prime weighted by gamma. Now, the only thing that we need to add is actually to think that in reality, whenever you're taking your action A from state S, you're not necessarily guaranteed to be in this particular S prime. There are many possible states where you can end up, and you need to average across all these possible states, again, depending on the probability to end up there. So we will now look at all possible states S prime where you can end up, and we will look at the likelihood of actually getting to this particular state. And our transition function would tell us what will be that likelihood. So again, there are two parts to it. One is we are taking into account how likely is to end up in some state S prime, and within it, we are collecting the immediate reward, plus we are looking at the value of the future state discounted. Okay, so here we just defined our, and let me add the stars here, our optimal stars. And now let me just define V in a similar fashion. So what I want to do is define V recursively, meaning to define V of this state in terms of V's of neighboring states. So here we are writing V of the state. And you remember that based on our formula, V is just max over all the A's of Q star SA. So what I can do, I can just take this expression, and instead of having here Q star, I would write what we already estimated. I'm just going to copy this whole expression. So we're going to have max A And then instead of having Q star SA, I'm going to write this full expression. And let's see what we will get if we do that. So now we actually got here the full expression for V of state S in terms of other states where you can end up going after the state S of the neighboring state. So those equations are called Bellman equations. And let me just show that we finished the Bellman equations. And these equations will be key for us when we are defining an algorithm for computing our MDP policy. So now with all these notations, we are ready to start talking about value iteration algorithm, which would enable us to solve MDP given the quadruple of state, action, transition, and rewards. And that's where we will utilize all these notations from above. Let me just start writing. So I will introduce a tiny bit of notation, so it's not a new notation, but I will just look at this value of the state. And when I introduce you a value of the state, I told you this is the expected reward that you're going to get when starting in the state S and acting optimally. I didn't tell you for how many steps you can go, for 1, for 2, forever. Until you are done. So now I would actually cap it up. I would say that this will be an expected reward that you can get after you took K steps. Okay, so we will introduce this new notation. This is expected reward from state S after K steps. And the idea here is the following. What is the connection between this Vk and my original V value of state? That when K goes to infinity, we would say that our Vk would actually converge to the true value of the state. So the recursive algorithm that I will define will at each point continue increasing number K until we will hopefully converge to the true value of the state. Okay? So how this algorithm will work? During the first step, this will be initialization step. We will make all of our value V0, they all will be equal, let's say, to 0. Okay, and if you need an intuition of what this Vk means, okay, Vk star means, you can think progressively about our original diagrams that we had, and I will draw you this diagram again. Okay. And what you can think about is, you can think about the information from the steps, from the states where we get higher reward. It will be slowly propagating around the board. And the first time we're going to look just in one step, then in 2 steps, and so on and so forth. So, and we will continue until we reach convergence. So our next step would be to say continue, iterate until Vks, roughly speaking, equal to Vk plus 1s for all s's. So we will continue this process until the values of the states do not change after every iterations. And what we will do, we will define the value of our step of our state at the point k plus 1s in terms of the values of the states through the previous iteration. So we computed the optimal values after k steps, and now we will aggregate this information to get the value for the step k plus 1. And that's exactly the formula that we wrote over here with the corrected parentheses is going to come handy. Because here, whenever we are going to be looking at the value of the state after of the neighboring states, we can actually take the values that was collected after k steps. Okay, so we are going to say that the value that we are getting after k plus 1 steps is going to be whatever we are collecting from an extra step plus the values of the neighboring steps after k steps. So let's just write it down. It will be much more clear than just talking about it. So we're going to say max A and I am pretty much copying the formula as it is with parentheses. And now I will take the values that I have already collected, which is the value of the neighboring state S prime after k steps. Okay? So this is the whole value iteration algorithm. Let me just very briefly illustrate to you what it will be doing on a very simple and trivial example. Okay? So let's say I am given now some very simple world, and we have several, let's say 5 states, okay? And you will collect your reward, you know, in this final step. When you get here, you collect the reward and you're done. You cannot move anywhere. And you also assume, again, it's a very simplistic state, that you are always moving deterministically, that you can only take one single action, okay? And whenever you take this action, you're going to end up where you want to be. It's very, very simple state. In reality, obviously, it doesn't work, but here we can say we would only move in the right direction, and we always end up where we want to be. And I would assume that gamma is equal 1/2, okay? So what I told you earlier, that during the step 0, all the v's are going to be equal to 0. That's how I start. I initialize all the value of the steps to be 0. Now, during the next step, what I am going to be doing, I am going step by step, and I am trying to see how my value is updated. It doesn't matter in which order I start doing it, correct? Because here you don't order the states in any way. Why it doesn't matter? Because we'll be only looking at the values of the previous iteration. So therefore, it doesn't matter if I start computing V1s from here or from here, it's exactly the same. So let's say I am here and I want to compute value of the states going somewhere by 1 step. I'm allowed just to walk 1 step further. So in this case, if I go 1 step further, then the value of that step is going to be 0. Okay, I'm not collecting any reward there because there is 0 reward. So this becomes 0. And the value of the state stays exactly 0. Nothing changed. And similarly, if I'm continuing walking and walking and walking 0, 0, 0, the only place where something is going to change is going to be the last step. Why? Because I know that whenever I try to walk right, which means that I'm staying in the same place, I am going to collect this reward. This is the reward that I would collect when I'm trying to go right, and I'm staying in the same location. So now this step, because of this value, becomes plus 1. And let's say it's a halting state, meaning that I cannot go back and forth and increase the number. Once I collected it, I cannot do it again. It's like if you got A in the class, you can just do it once for the same class. So now we can look at how the value change when we are allowed to do 2 steps of within our iterations. So here, let's again start in the order here doesn't matter, because when I'm looking at the value of neighboring states, I'm just looking at the previous step. So here, nothing really changed because the neighbors are still 0, okay? So here we're going to see some interesting development. First of all, as I told you, from this state, whenever we go right, we collected the reward. I requested that once we collected the reward, we cannot get it again. This state is going to stay plus 1. Now let's see what happens here. This is an interesting state where we see some development. So we will go right because we're just allowed to take one action. We're going to go right. We will not collect any reward because I didn't provide any reward when you are jumping. However, this is the part that gets activated because the VK, the V1 of the previous state is plus 1, and I will multiply it by my gamma, which is half. So in this case, the value, of the state is going to be 1/2, okay? And we can continue now. And if we will continue, we can again see how this value will continue propagating. I will not do this complete computation and it will be left as an exercise, but you would see that with every step, the number of non-zero entries is going to increase and the values here are going to increase until at one point we will not see any change. Now I want you, of course, to remember that this was really a baby world where we are always certain where we go and we have just one action to take. Never happens in reality. And in this case, we will see much more complex interaction between the values because you can go in different directions, so they will start really impacting each other. The fact that we stabilized here and it doesn't change is just a side effect of a very simple world that I designed you, but it shows you the high-level intuition. We will start with the states where the big reward or punishment allocated and they are going to propagate it all around, and we will continue until convergence. So I want to talk to you a bit about convergence because you can ask me, how do you know that it's going to converge? And I will not do the full convergence proof here. I want to look again in a very simple world just to give you an idea how the full-scale proof may look like. So we will talk a bit about convergence now, okay? And the world that I will look at convergence would be similar to this world, even simpler. I would assume that I have a single state S and a single action A, okay? It's like really a baby situation. Okay, so what I would know if I have just a single state, that V star of K plus 1 of this state S, correct? So there is no max because we just have one single action. It's going to be RS plus gamma V star KS. Okay, so let's just see that we understand. Again, we don't need to average over different possible destination because we're going to end up always in the same state because we just have one state plus gamma and the value of the state after k steps. Okay, now what I also know from if I am already converged, when we totally converged, this is a situation that we underline here. You remember when our number of k steps ran to infinity, and now we have true values of the state. What we know is that when I am in the converged state S, that when I take my next step, nothing is going to change. So I also know that it's equal to V star S, because this is my stop condition when we don't continue, when my previous iteration, the current iteration, have very close values. So now what I will do, I will subtract the converged value from the value in k plus 1 iteration, and similarly the converged value from vk, and I will compare them. Okay, so what I'm going to do is actually take the first row and subtract it from the second. V star S minus V star k plus 1 S equals gamma V star S minus V star KS. So let's look at these quantities. Here we are looking at the difference between the converged state and the value at step k plus 1. Here we are looking at the difference between converged state and the value after k step. And what we see that at every single step, the difference between them is determined by this gamma, which is the value between 0 and 1. So what it means is that at every step, the distance between our computed value k and the true converged value v is decreases, and gamma will determine the rate with which this decrease will happen. So, and this is kind of a baby case, but you don't have to look into how this may be working in a more complex scenario, but this is exactly the same intuition that shows us as we continue and increase the number k of steps, we're getting closer and closer to the values v, which are optimal values v. Now the next step for us, hopefully I convinced you that this algorithm will converge, and if we will continue doing enough of this interaction, at some point we will stop. But now you may be asking yourself a question, okay, now I have v, how do I actually act, correct? Because value v doesn't tell you what you should be doing. And at that point, to decide what you should be doing is actually, I want to bring back our Bellman equations again and remind you that in this case, we can actually compute all the q's. Given v's, we can compute the q's, correct? Because q's are defined in terms of v. And once we computed all the q's, we can actually, for every state, find the best possible action. That's what we will do. So the next step, when we completed this algorithm, we will compute for every state S and for every action A, we will compute the Q values. And once we have all the Q values computed, we can actually say that the action S that we need, the action A that we need to take in state S will be just argmax A Q star SA. What it says, for given state S, go select, check all the Q star SAs and select the action which maximizes it. So what eventually I got after this algorithm, when it converged, I computed the Q values and then I computed the policy. And now I know how to act in my MDP. So that's what we have done here. One question that you may be thinking about is, this is kind of strange. I go through the mess of computing all the V values, then I am computing the Q values to get the policy. You can be thinking, why wouldn't I directly compute the Q values? And this is indeed a very valuable question. Exactly the way we computed this value iteration algorithm, we can directly operate at the language of Qs. and do exactly the same computation and directly get Qs. And that's exactly what you will do in your exercise. You will reformulate this algorithm and get a new algorithm which is called Q value iterations. But the idea is exactly the same. And we will use this algorithm in our discussion about reinforcement learning next time. Thank you.